Maybe you've watched the curved, sine wave-shaped textile curl into something resembling a Brutalist-era lounge chair, or the Eiffel Tower miniature of a gelatine makeup gone flaccid, recovering shape when exposed to heat during a curious Google search. These mighty morphing objects are renderings of 4D printing, a new science that introduces self-activation properties to 3D printed objects. With 4D printing, objects can be printed with extra features that allow them to change shape or function over time, said Cindy Snow, an assistant professor of mechanical and manufacturing engineering at Miami University. This could be used to create objects that can adapt to their environment or even self-repair. In today's video, we are going to show you what is 4D printing and how does it work. Without further ado, let's begin. What is 4D printing? A kind of active origami. 4D printing creates self-assembling, programmable matter designed to temporarily transform. Essentially, the fourth dimension stands for time. So in terms of a printing application, 4D projects are basically time-dependent 3D printed renderings that morph in response to environmental stimuli they interact with once fully fabricated. By definition, this is done with no human or mechanical intervention. That's kind of the whole point. Skylar Tibbetts, founder and research director of Massachusetts Institute of Technology's Self-Assembly Lab, described the objective of 4D printing: to create motorless, wireless, powerless tech, when he first coined the term during a TED Talk in 2013. What we're really trying to make is robots without robots, Tibbetts told Fast Company. We want to design materials that can transform themselves when exposed to energy, but which don't necessarily require circuit boards, electronics, or other moving parts to operate. The shape-shifting, smart materials that make up 4D printed items react to a catalyst, such as heat, water, light, wind, or electricity, based on a set of instructions written into their geometric coding. They may elongate, bend, wrinkle, fold, twist, or even disintegrate once activated. Anything from wood to rubber can be stratified with stimuli-responsive materials. The purpose of this practice is to discover new properties. Four-dimensional printing has lots of potential influential application areas, Cho said, listing medical, flexible electronics, soft robots, and even furniture as use cases. How does 4D printing work? Equipped with commercial 3D printers, researchers begin by inputting smart material, also known as metamaterial. These textiles, which hold the transformative properties unique to 4D objects, are commonly crafted out of hydrogel or shape memory polymers. Hydrogels are responsive to moisture, while shape memory polymers have the ability to bounce back to their original state after deformation. The simplest example of these would be a sponge, a material that changes shape when pressure is applied, said Vineeth Venugopal, a materials engineer at MIT. A more complicated example, he said, would be a shape memory alloy, such as nitinol. Made out of titanium and nickel, it can spring back to its original shape after any sort of deformation. These animate materials could totally change our world. These animated traits can be credited to a geometric code pre-programmed into the material. According to its instructions, the printed object will activate once triggered by a set stimulus occurring naturally in its environment. These are called smart materials, said Venugopal, and if a recent report from the United Kingdom's Independent Scientific Academy, Royal Society, is to be believed, these animate materials could totally change our world. Building with materials that have active, adaptive, and autonomous properties would be a game changer across sectors. The Royal Society report notes, most noticeably in industries like construction and transport, as well as medicine and textiles. Matter that changes when it interacts with electric energy. Piezoelectric. These react to applied mechanical stress, such as pressure or latent heat. Thermoreactive. Heat or temperature fluctuations transform these materials. Photoreactive. Materials catalyzed by light. Magenta reactive. Elements that transform when interacting with magnetic energy. pH reactive. Matter that's triggered by pH levels. 3D printing versus 4D printing. Four-dimensional printing is the next step up from 3D printing Teo said, noting that you can't have one 4D without the other 3D. Differentiating between the two starts with establishing the base of both technologies. Three-dimensional printing is a rapid prototyping technique, commonly referred to as additive manufacturing, that deposits material layer by layer to fabricate three-dimensional objects. This same mechanism is used in 4D printing to create parts. The bonus dimension that distinguishes one from the other, however, is determined in an object's geometric coding, as detailed above, which takes that extra step before pressing print. Here, researchers encode the object's desired functionality based on its angles, measurements, and dimensions. So just as 3D printing is about adding depth to a 2D structure's limitations, 4D is about adding one more factor to the dimensional composition: time. More specifically, change over time. While 4D printed objects will morph into some sort of action, 3D printed renderings maintain their static, rigid form. Four-dimensional printing is able to create objects that can change shape and size after they have been printed, whereas 3D printing is a more basic form that can only create objects with a fixed shape, Teo said. It is a creation other than the application. 4D printing examples. Not yet commercialized, innovations in 4D printing are still restricted to research and laboratory experimentation. Any applications that are taking place, such as a breast implant that allows healthy tissue to grow in a cancer patient, are considered highly experimental anomalies that before widespread usage are pending substantive testing and government approval. It's important to note, though, that the groundwork has already been laid. Real-world use cases of 3D printing will foreshadow what's to come: biomedicine. The example above, featuring a biodegradable 4D breast implant, is an example of tissue engineering pioneered by researchers at Chiang-Jiaotong University's National Lab. This particular application has developed since, using cellular adhesives known as scaffolds, or biomaterials engineered to promote cellular growth in the formation of new functional tissues. Stents. Two types of 4D printed vascular stents, temporary tubular supports, often made out of metal mesh, stitched into vessels to promote blood flow, are being explored with the application of shape memory. A genetic algorithm is coded into the object, which then simulates a healthy blood vessel by rapidly expanding narrow pathways, researchers from the Harbin Institute of Technology in China have found. Military. MIT's self-assembly labs have developed a morphing jet engine air inlet prototype out of programmable carbon fiber. Unlike its mechanical counterparts, this model is lightweight, minimizes accident-prone mechanisms, and operates independent of electronics, sensors, or actuators, according to Air University researchers. So guys, let me know your thoughts down in the comments section below. Give this video a thumbs up for more interesting content. And don't forget to subscribe to the channel for more awesome content. Have a nice day, and I will see you in the next video.